Okay, well, let's learn what we've just used to see if we can understand why there are two types of superconductors, type 1 and type 2. Here, let me go to the notebook. All right, so it turns out there are two important length scales inside a superconductor. The first is the coherence length. Which we've already talked about. Okay, and that governs the size of a pair, if you like, but it's also a length scale on which, well, the density of pairs can't really change on a length scale that's shorter than this. Okay, so if we have a high density of superconducting pairs in one part of a superconductor and a low density elsewhere, the concentration can't change too quickly. It can't change any faster than the length scale governed by the coherence length. The other is called the London penetration depth. The London penetration depth tells me approximately how far magnetic fields can penetrate into a superconductor. So we said that magnetic fields go to zero inside a superconductor normally, but they don't just go instantly at the edge of the material. They drop off over a length scale, and the length scale is called the London penetration depth. And it comes out of using electromagnetic theory, combining that with the Meissner effect. Okay, it's worked out by London. In any event, the London penetration depth tends to be of the order of 50 to 500 nanometers in different superconductors. Okay, and it's the penetration depth for the magnetic field. Whereas, as we said, the coherence length tells me how fast the concentration of pairs can change. Okay, now I wanted to mention these because there's something important about type 2 superconductors. Okay? Remember what happens in a type 2 superconductor when we're above the first critical field? Here, let me make a sketch. Here was our picture. We could get this kind of vortex structure, where in the center, a flux quantum, magnetic flux penetrates through the superconductor in the form of a flux quantum. Around the flux quantum, we have a region which is normal, and then that's surrounded by a sheath of circulating supercurrent. Which screens out the magnetic field in the remainder of the superconductor. And what's interesting about this structure is that this structure can only exist if the London penetration depth is larger than the coherence length. Okay? Think about this. In order to have this structure, the center has to be normal. All right? And then the material has to become superconducting again within a region such that so that the magnetic field can still penetrate into the superconducting area a little bit. So we need a normal region for the flux quantum to go through. And then we need the superconducting sheath here. So there still has to be a finite magnetic field there so that we have a supercurrent to cancel it. And then we can move out into the superconductor. So in order to have this structure, we need the penetration depth of the magnetic field to be larger than the coherence length. And therefore, type 2 superconductors are those superconductors in which the London penetration depth is greater than the coherence length, whereas type 1 are the opposite. Okay? It's kind of a neat picture. Now, moving back up, notice how the coherence length depends on the size of the gap. It goes inversely with the size of the gap. So that means materials that have a high transition temperature and therefore have a high gap will tend to have short coherence lengths. Those will tend to be the type 2 superconductors. Whereas materials with low transition temperatures will have a small gap, and thus they'll have large coherence lengths, and they'll be type 1. So, oh my goodness. Here we are. So usually materials with a high TC are type 2, whereas those with a low TC are type 1. But it depends on this other quantity, the London penetration depth, so that pattern isn't always strictly followed. All right, well, that's a neat result that we can take from what we've learned so far. There's one more thing I'd like to talk about before we finish. I'd like to talk about flux quanta. I think I'll put that into a separate little video. So let me stop this one.